All right. Hello, hi, good evening, everybody. Welcome to this brand new session of NEET 2022 One Shot Series. Yeah? So, how are you all doing today? Hello. All right. Tell me in the chat, am I audible? Am I visible? Yeah? Tell me in the chat window. Hello, Ifat. How are you doing today? All right. Good evening. I can see Muthu Lakshmi. Hello. Tell me, am I audible properly? Am I visible properly? Okay. I can see Prashant has joined as well. Good evening, Prashant. Hello. Hello, Yasir. All right, Muthu Lakshmi, thank you for, well, confirming that. And I am doing good. I'm doing good. Ifat, how are you? How are you guys doing? How is the preparation going on? I know. Now that the date has been announced, everybody is on edge, right? Yes, I can totally understand that. But what are we doing? We are preparing with full speed. So guys, keep doing that, yeah? Keep attending the sessions, keep practicing at home, and as I've told you, always practice with time, especially physics, right? Because there are a good number of, yes, calculation-based questions as well. So, I can see a lot of people have joined here as well. Hello, Kiran. Good evening. Hello, Anjali. Hi, Rajshri. Hello, Soumya. Hi, Pratihar. Good evening. All right. Hi, Vanishka. Good evening. I hope you all are doing good. And I hope you all are ready to start modern physics. Yeah, I mean, modern physics is one of the most scoring chapters, right? One of the most scoring entire unit. So not only this chapter, today we are starting with dual nature of matter and radiation, and not only this chapter, the entire modern physics. So, as I think you would have seen my strategy session, I had a couple of weeks back, I had given a strategy session where we were talking about 50 days strategy for NEET preparation, right? And there as well, I had given you some chapters, some units, from which really easy and medium level questions come, right? Now, entire modern physics falls in that. So, guys, please buck up and make sure you pay full attention to modern physics, okay? Now, when you look at it, when you first hear about it, it might seem a bit intimidating, thoda difficult lagne lag jata hai, but don't worry about it. It is very, very easy to understand, right? Depending on aap kaise pad rahe hain. Here, we are going to understand from the basics and understand the applications properly, okay? All right. I can see many more people have joined. Hello, good evening, Guddu. Good evening, Prem. And hi, Vedant. Hi, Vaishnavi. Hello, Ehsan. Yes, आज बहुत मजा आने वाला है. आज हम modern physics की start कर रहे हैं. All right. Now, without further ado, let's start and let's get going. Okay, dual nature of matter and radiation. Now, in this particular one-shot session, these are the subtopics that we are going to cover. All right. So, let's start with it. First subtopic is nature of light. We're going to understand little bit what's the nature of light, photon theory. Then we'll go to de Bruys hypothesis, Davison and Germer experiment, and then we'll go to Heisenberg's uncertainty principle. Okay. Right. Let's get started with the first subtopic of today, which is nature of light. And see, nature of light, we have understood a lot about light till now, right? Come on, last two sessions, we had optics. Optics is all about study of light, right? So we studied geometrical optics, we studied ray optics, and we studied that light exists or light exhibits both particle nature and wave nature, right? We've understood that. All right. Hello, Sakshi, you're here. Hi, Janani. Hello, Prashant. All right. Good evening, MBBS lover. आपके तो नाम में ही MBBS है. Great job. Okay. Sunny, hello. Hi, Vaishnavi. All right. Let's continue with this. Nature of light. So, Now think about it. There are certain terminologies, there are certain things associated with light, right? Which is what? Light, since it's a wave as well, there is wavelength, frequency, speed of light, intensity of light. Intensity of light depends upon the source, right? How bright the source is, so to speak, right? Think about it that way. Energy of light, energy, how much energy is being given, right? At the end of the day, light is a wave, which is what? Propagation of energy. So, energy and power. Power is energy per unit time. So, for light as well, energy per unit time is power. Now that we know these basic things about light, let's see what we've already done in geometrical optics and wave optics. Alright, we've come to certain conclusions by now. So, we have seen that light exhibits different phenomenon based on different nature. So, here we can see that, well, reflection of light. Reflection of light confirms wave nature as well as particle nature, right? Refraction of light, again, wave nature, particle nature. Both natures can explain refraction of light. Interference of light, on the other hand, right? Interference of light happens when light is exhibiting wave nature only, right? It's exhibiting wave nature. It cannot be explained by particle nature. Diffraction, again the same thing, wave nature of light. Polarization is explained by wave nature of light. But then if we talk about other phenomenon which we haven't studied till now, photoelectric effect, black body radiation, we are going to cover it tomorrow. But here in these cases, light exhibits particle nature, right? So we understand that light, well, there is dual nature of light, right? There is wave particle duality in light. Dual nature of light, what does it hold? It holds that light exhibits properties of both wave and particle, and light exhibits property of either wave or particle at a given time. This is important to understand. Alright? So at any given time, at a particular experiment, say you're performing a certain experiment, you have a setup, light is going to behave either like a particle or like a wave. Okay? Not both at the same time. Alright, I hope all of this is good. Alright, Ifat is saying, ma'am, clear nahi dikh raha hai. What happened? Can you refresh? Maybe you will get to see clearly. Can everybody else tell me, am I visible properly? Am I clear to you guys? Give me a thumbs up in the chat window if you can see me clearly. Okay? Come on. Alright, I can see that you've refreshed and you can see me clearly. Hi Bikash. Well, now that the session has started, let's get going. Yeah? Okay, thanks Kiran. Little unclear, huh? Check your internet connection. No, it might be that. Because I can see a lot of thumbs up here. Clear hai. Alright. Now that we've understood, well, light exhibits dual nature, right? Let's go and explore a little bit more about particle nature and how that comes to be, right? And to explain particle nature, we have photon theory of light, okay? Photon theory of light. Let's see what that is. So, the idea here is that, well, all of this, right? The birth of modern physics happened with, yes, Max Planck. Max Planck is the father of modern physics. You all know that, right? So what happened with him? He said he gave his own quantum theory in 1900, right? And he said that energy of light depends on, it's directly proportional to the frequency of light. All right? Energy of electromagnetic waves is directly proportional to frequency. And he also said that this energy comes in small packets. Or rather, after Planck's theory, Einstein took this, he did his own calculations, and in 1905, we ultimately got quantum theory of light. Alright, and what does quantum theory of light say? Quantum means single, right? A unit, a single unit. So, we'll say that quantum theory of light says that energy of light comes in the form of quanta, right? It comes as small units. It comes in the form of small packets of light. All right. So how can we think about it? Say for example, think about it like you can see water, right? All right. So say a tap is running and there is some water that is flowing. Now, see here. If a tap is running and water is flowing, you can see that flow of water and you can say that, all right, there's this water flowing, right? But this water that comes out of the tap, that water has small molecules, right? So you will find water coming in quanta of molecules, right? There will be n number of molecules at any given time that will be there in the flow of water. You can't have half molecule anywhere there, right? The same way, when light flows, or rather when we see beam of light where we say कि all right, light आ रही है and we have a certain intensity. Say for example, यहाँ पे मेरे पास light लगी हुई है, right? ये light आ रही है मेरे पास, and what I'm able to understand is बहुत सारी light आ रही है. But if I go further, if I go in a very small level, right, not even microscopic, very small level, I'll be able to say that light is coming in small packets of energy. Okay, so if light is coming, say for example, यहाँ से light आ रही है, and if I have a detector over here, then if this detector is able to detect energy very minutely, then it will be able to detect it in this kind of a scenario. एक बार में this energy came, then this energy came, then this energy came, and so on. 0, 1, 0, 1, 0, 1. This way. All right. Okay. So now that we understand that light comes in packets called photons, right? So these wave packets are quanta. They are called as photons. And then obviously, if I say that light energy is coming in the form of, well, photons, then it is individual particles, right? It is coming in the form of individual particles, or rather we can say that this is depicting particle nature of light. All right. Now, obviously, when we have, well, photons coming with a certain energy, they will have certain energy and certain momentum, right? And then again, Einstein's photon theory also gives us those values. What is the energy of one photon? What is the momentum of one photon? So let's understand more. Let's see what that comes about. All right. Now, we understand that these are photons of light, right? And light travels with speed of light. So these photons, they'll also travel with speed of light. Simple? All right. So speed of photons will always be speed of light in vacuum, which is 3 into 10 raised by 8 meter per second. And energy of a photon, as well given by Max Planck, energy of a photon is directly proportional to the frequency. So E is directly proportional to frequency, and the proportionality constant is Planck's constant. So this H is Planck's constant, right? The value of H is very small, and that will tell you how small that energy quantum is. Okay, see, value of H is 6.626 into 10 raised by minus 34 joule second, right? So if I say that there is a light of, say, frequency, well, 10 megahertz, right? So if there is light of frequency 10 megahertz, which is what, 10 raised by 7 hertz, I am still going to get a really small value of energy, right? So what does this come about? This comes out as 6.626 into 10 raised power of minus 27 joule, right? Of the order of 10 raised power minus 27, right? Just an example. That gives you how small is the value of energy in one quantum of photon, right? In one photon. Okay. I hope this is clear. Now, when we talk about energy, well, since E is equal to H into nu, and we know that for any wave, not just electromagnetic waves, right? V is equal to F lambda. So here as well, we can say that velocity is C over here. So C is equal to F lambda, and energy comes out to be hc by lambda, right? Just by simply understanding the wave relation. So E is equal to hc by lambda and E is equal to h nu. Remember this to calculate energy of any given photon. All right. And well, just to remember a shortcut, I will say that if you substitute the value of wavelength in angstrom and substitute the value of h, E is equal to 12400 divided by lambda gives you energy in EV, alright, electron volts. आगे जाके later on in calculations, this is very important, right? You know that in exams you have to do very quick calculations, right? And in modern physics, the entire chapter, there is a good amount of calculation involved. So do remember this short calculation trick, alright? Okay. Energy in electron volt is equal to 12400 divided by wavelength in angstrom. Alright. This is about energy of a photon. Let's talk about, yes, momentum of a photon. Right. So any photon out there, well, it's depicting as particle nature of light, right? So particle is traveling. If particle is traveling, it's going to have certain speed and certain momentum, right? Now, mass of a photon is 0. So when we talk about momentum of a photon, we get momentum of a photon from special theory of relativity. Alright. Now, special theory of relativity is not there in your syllabus. That is why I am not going to go there. But wahan se very easily you can derive this. Alright. So, momentum of a photon comes out to be h by lambda. H is again Planck's constant. Lambda is wavelength. Okay. Do remember this. Now that we've understood this much, right? Let's understand properties of photons more. Okay. So, what are properties of photons? First of all, energy and momentum of a photon are always conserved, right? So, once there is a packet of light that is released, that packet of light will keep going, right? Now, you know that for any wave out there, right, not just electromagnetic waves, for any wave out there, once the source has released that wave, the frequency of the wave is not going to change, right? So, energy of a photon is h nu. If h is a constant and nu does not change, then why would energy change? Make sense? Energy will not change. So, energy of a photon will be conserved. Okay? Alright. Now, when we talk about number of photons, right? So, now again, think about it. If there is a light source and you change the intensity, you dim the light source or you increase the intensity of the light source, right? The number of photons coming out might change, but until you change the frequency, the energy of the photon is going to remain conserved. Okay? Alright. Now, another property, all the photons of a particular frequency or wavelength possess the same energy irrespective of the intensity of the radiation, right? So what does this mean? It means that, say you have a particular source, particular light source, right? So what is happening? As long as the frequency and wavelength remains the same, right? So this light, if it is giving out photons of the same frequency and same wavelength, that means all of the photons that are coming out of this light source will have photons of same energy, right? So when we say the energy comes in packets, it is actually packets of equal energy. All right? बराबर packets, equal packets में energy distribute होती है. All right. Irrespective of the intensity of the radiation. That means whether you dim the light or make it brighter, it doesn't matter as long as you keep the frequency and wavelength that particular value. Okay? Alright. Now that we've learned this, let's go to the next one. Increase in intensity of radiation implies an increase in number of photons crossing a given area per second. Right? So now again, think about the same light source. Say I have a monochromatic light source. Right? And what do we mean by monochromatic? It's giving out light of particular frequency, particular wavelength. Right? We've learned it in wave optics. Okay. So there is a light source. Now again, as I've told you, if I reduce the intensity, right, that means it will give out less number of photons, but the energy of individual photon will remain the same. Similarly, if I increase the intensity, it will give out more number of photons per second, right, per second per unit area. That is what intensity is. Energy per second per unit area. Okay. Next, rest mass of a photon is 0. right? And here, since we are not going into relativity at all, we will say that for simplicity, mass of photon is 0. All right? Keep that in mind. We are not going into special theory of relativity. All right, so for all intents and purposes, for our syllabus, mass of photon is 0. All right. Now, charge on a photon is also 0. Of course, photon does not contain any charge whatsoever, does not contain any mass whatsoever. It has only energy, that is traveling with speed of light. All right. Now that we've understood what photons are and what are the properties, how they behave, let's move ahead and understand more, all right? And here is the scenario. So, as I told you, now that we've understood photon theory, we'll go to de Bruys hypothesis, okay? And yeah, I mean, de Broglie is how we learn to pronounce it, right? I also learned it the same way in school. The thing is, he was a French guy. French people, weird names, you know this. So what happens is, he's called de Bruy. Cancel all of this and write away. De Bruy, right? Okay, so the idea here is, now how is our understanding of science progressing here? See, in 1900, Planck gave his quantum theory, right? Yes, and then, of course, Einstein did his own calculations, added to it, we got the entire photon theory, right? Okay, so now we understood that light behaves as particle, light behaves as waves, and we had all of these calculations, right? We understood that yes, light sometimes behaves as wave and sometimes behaves as a particle, and the energy of light comes in quanta of photons. But then people started wondering the other way around as well, right? That if wave, which is electromagnetic wave, right? Electromagnetic wave, if it can behave as a particle, can the other way around also happen? Can a particle also behave like a wave? Right. And that's what came about with Victor de Bruy. All right. So Victor de Bruy gave his own hypothesis. We call it as de Bruy hypothesis, where he said that not just electromagnetic waves, right? Not just light, but everything, all matter under the universe, all matter will behave as particle as well as wave, right? So he said that this is not just there for one particular type of wave, or rather not just true for light. This is true for all matter out there. And he gave his hypothesis that yes, any moving particle, not just the photons, but any moving particle of matter should also display properties, wave-like properties, right? And this wave, right, that he associated with matter, they are called matter waves. Now, how did this come about? I mean, what else did he say about it? So, the idea here is that the wavelength associated, now, once he gave the wave, he gave the wavelength of those waves as well, right? So, what he gave was the wavelength associated with a moving particle, yes, it is known as de Bruys wavelength, and that lambda is equal to h upon p. H is, yes, Planck's constant, p is momentum of the particle. All right. Now, here's the beauty of it. See, for a photon also, right, for a photon as well, lambda is equal to h, or rather we calculate, or we learned about momentum of a photon, right? So p is equal to h by lambda. If you actually interchange them, we get lambda is equal to h by p, right? So this is true for a photon, and what he did was he took the exact same expression and he gave it like this, right? But there was a lot of other theory behind this, right? And later on, with Davison and Germer's experiment, this was proven as well, right? And that's what makes it completely revolutionary when it comes to modern physics. So, not only we understood that light actually comes as energy packets or photons, light behaves as a particle, but we understood that all matter behaves as particle as well as waves. Wave-particle duality, not only for light but for matter and radiation, everything out there. Okay, so we understand that for any particle out there. Now think about it this way. If we know the momentum of a particle, then we can find out de Bruys wavelength, right? And if we know the kinetic energy of a particle, since we are talking about mass right now, we will know, yes, if we know kinetic energy, we know mass, we can find out momentum as well, right? Come on, kinetic energy is p square by 2m, momentum is equal to root over of 2m kinetic energy. You know this from basic mechanics. So now here we can say that we can find out, for our calculations, we can find out de Bruys wavelength when momentum of a particle is given or when kinetic energy of a particle is given. Alright? So h upon root over of 2m into kinetic energy, this is de Bruys wavelength. Now, what about charged particles? Well, if there is a charged particle and it is accelerated through a potential difference of v, then we understand that it gains certain kinetic energy, right? Of course, we've studied it in electrostatics. So, the charged particle will gain the kinetic energy equal to q into v. And that's about it. You substitute the value of qv in the previous equation, you get the next equation. Simple? Tell me if everything is clear till now or not. Okay? If there's any doubt, ask me right now, because now that we've understood the fundamentals from the basics, we will go and solve questions. Come on. Alright, here's a question for you, and yes, it has come in AIPMD before in 2014. Quickly solve the question, quickly give me answer in the chat window. Alright? Okay. Alright Kiran, I can see that you are understanding everything. Now quickly solve this question. I'll read the question for you. If the kinetic energy of the particle is increased to 16 times its previous value, the percentage change in de Bruys wavelength of the particle is. Okay, Yash has given an answer as well. C. Alright, let's see what the answer comes about. Others also solve. I can see Anuj has also given answer C. There are 4 options, as you can see, 75, 25, 60 and 50. And you can see that it's again a very basic application of the relation that we just studied, right? Exactly. So, should we start? Alright, Ifat has also got C. Come on guys, quickly solve. Give me answer in the chat window. Alright, Janet's getting A. Kiran got C again. Alright, Zuha got C, 60. Good job. Okay, shall we go to the solution? So, we are talking about kinetic energy of a particle, right? Change in kinetic energy of a particle, percentage change in de Bruys wavelength. So, what are we talking about? We're talking about relation between de Bruys wavelength and kinetic energy. And we got that relation just now, right? Of course, we can directly apply lambda is equal to h upon root over of 2m into kinetic energy. Basically, lambda is directly proportional to 1 upon root over of kinetic energy, right? Okay, so what do we see? We can say that since every other value does not change, h is a constant, it's not going to change, mass of the particle is not changing, right? So, new lambda, lambda dash square comes out to be, yes, in the denominator, we've got 16 kinetic energy, right? Of course. So, 1 upon 16 lambda square. But then, we want the new wavelength. New wavelength comes out to be 1/4 of the original wavelength. So, how much is the change? Of course, percentage change comes out to be, as you can see, percentage change will be 75%, right? Okay. So, if the final value is 1/4 of the original value, that means 3/4 of the value got changed, right? 3/4 change means 75% is the change. So, the answer comes out to be 75%, A actually. Okay. So, who got A over here? I can see Janet got A. That is the correct answer. A lot of people got C though. I mean, do you understand where you did the mistake? Where exactly did you go wrong? Alright, I hope you've understood this. Yeah? Okay, if I is saying -1, What is minus 1? Okay. Percentage calculation, nah? Yeah. Alright, guys, make sure calculation is okay, right? And this is where, again, I always say, practice with time. If you practice with time, give every question 1 minute to solve. Okay? You will not make mistakes in calculations. Alright. Pratyahar, to and by confusion. Yeah. So read the question properly. See, these silly mistakes, the more you practice with time, they will reduce. So that in the final exam, you do not make these silly mistakes. Okay? Alright. Now that we've understood this much, right? Let's go and learn more about matter waves. Here we are going to study about properties of matter waves, right? So what properties do matter waves exhibit? First thing, matter waves are related to moving particles and independent of charge of the particle. Okay, so matter wave is related to, yes, moving particles. It depends upon momentum of the particle, mass of the particle, velocity of the particle, but does not depend on charge of the particle. Alright. Now, second is, wave and particle nature of moving bodies are mutually exclusive. Right. So just like in light, we studied dual nature of light, right? But they exhibit one or the other at a given time. Here also in matter waves also the same thing happens. What? It is mutually exclusive. That means they can never be observed at the same time. It's either exhibiting particle nature or exhibiting wave nature. Now, matter wave represents the probability of finding a particle in space. We will look at more about this in Heisenberg's uncertainty principle. Alright. Wave nature of matter is significant when de Bruys wavelength is comparable to dimensions of the matter. Alright. And to understand this more, let's take a quick example and see we have got two particles. Alright. One is a baseball and another is an electron. Okay. Now think about it. For a baseball, mass is 138 grams, speed is say 30 meter per second, right? You've got a bowler who's throwing the baseball with a good amount of speed. Mass for an electron is 9.1 into 10 raised per minus 31 kgs and speed is 3 into 10 raised per 6, say. Alright, meter per second. Now with these different dimensions and speeds, right? If we look at their de Bruy wavelengths, what do we see? For the first one, when we calculate h upon mv, we get lambda is equal to 1.6 into 10 raised per minus 34 meters. See how small it is. And in the second case, when we calculate, we get lambda is equal to 2.42 into 10 raised per minus 9 meters. Right? Now, the idea is that if wavelength of the matter wave is comparable to the dimension of the particle, then it will exhibit wave nature predominantly. Otherwise, particle nature. Okay? So here, wave of, well, baseball. De Bruy wavelength of baseball is very, very small compared to its dimensions, right? The baseball is yay big. So, here, in case of baseball, no, wave nature will not be predominant. Alright? But in case of electron, you can see that de Bruy wavelength is very much comparable to the dimensions. So, of course, it's comparable to the dimension of an atom actually, right? So, of course, wave nature of electron will be predominant. Okay. With this example, I think you can understand for a particle in a given circumstance, in a given situation, either it will be wave nature or it will be particle nature that will be predominant. Okay? Right. Now that we've understood this, let's go ahead and solve another question. Come on guys, quickly. You have only 60 seconds. Quickly solve this question. Tell me what the answer comes about. Alright? And in your attempt to do it very quickly, do not make silly mistakes. So, there should be a balance between solving a question very quickly and solving it accurately. Right. Now, I'm going to read the question. This is also a question that has been asked in NEET before, NEET 2017 question. And with these questions, you can see how easy these questions are, right? simple direct applications of the concepts that we're learning. So, the de Broglie wavelength of a neutron in thermal equilibrium with heavy water at a temperature of T Kelvin and mass m is. Alright. Well, Bikash got answer as A, and Kuldeep you're asking, did you teach class 10th? No, I'm not, I haven't taught class 10th. I have been teaching from class 11th and 12th. But yeah, actually I have been teaching math and physics both for, different classes. So I've taught math in 10th grade as well, science as well. Alright, it's all math and science, right? Yeah, subjects that I love. Alright, let's see. What about this question? Bikash, A, Yash, B, I think. Why, Yash, you're not confident? What about the rest of you? What do you think? What is the funda here? What does this mean? A neutron in thermal equilibrium with heavy water. What does that mean? Neutron in thermal equilibrium with certain heavy water, right? What does that mean? It means that if two bodies are in thermal equilibrium, then their temperatures are going to be the same, right? So here, what do we have? Here we have a question that is taking concepts of thermodynamics that you've learned in 11th grade, and it's mixing with, yes, modern physics, right? So here it means that this neutron actually is at temperature T Kelvin, alright? And using this, you can find the energy, right? Of course you can. Alright, here you can see that kinetic energy of a neutron when it is at temperature T is 3/2 kT. You know this, K is Boltzmann constant, right? So for one neutron, I will say that kinetic energy is this. Momentum is root over of 2m into kinetic energy. We know that. Here, just substitute the value of kinetic energy here, right? There we go. We get root over of 3m kT. Now this is momentum, and what is the value of de Broglie's wavelength? De Broglie's wavelength is h by p. So here we go. H by p, h over root over of 3m kT. Alright. I hope this becomes clear to you. So here, what has happened in this particular question? One very basic concept of thermodynamics is involved here, right? And a very basic concept of modern physics is involved. So your final answer comes out to be equal to what? Option number A. Everybody understood this? Alright. Okay. Abhinandan, Shruti, I see you understood. Okay. Yash, you are in 9th grade and you are attending this 12th grade class. Good for you, man. Alright. But do attend your own grade classes as well, right? Do not miss those lectures. Okay. Now, let's move on to another question. Alright. Shruti is asking how to increase the retention of basic formulas in memory. Shruti, there is one thing that I tell everybody, alright, and this I think all of you can benefit from this. So, the mind maps that we give, right, after every session, keep those mind maps with you, and those are basically your short notes, one page notes, okay. Keep those notes with you. I would say in hard copy, keep it with you in hard copy, and every night, alright, after you've done everything else, you're about to go to sleep, right, give 30 minutes to just go through those, that's all, okay. If you do this every day, right, one page per chapter. If you do this every day, go through these short notes every day, 30 minutes before sleeping. It will not require a lot of your brain power also, and you will keep everything in your head. Okay, it will create actually a mind map, a memory palace in your head, right? And I'll talk about more about memory palace and how to build a memory palace in, well, another session, okay? I will come up, I'll have a separate session for you with this. Now, let's move on. And here we have another question. Come on guys, quickly solve this question. If the momentum of an electron is changed by delta P, then de Bruys wavelength associated with it changes by 0.5%. The initial momentum of the electron will be. Come on, tell me what is the answer that's coming out here. Option A says delta P divided by 200. Option B says delta P divided by 199. Option C says 199. Option D is 400. Now here, look at options A and B. Yeah? Options A and B are very close, aren't they? Delta P upon 200 and delta P upon 199. Right. And when these options are really close and you're talking about small changes, right? Sometimes when we're talking about small changes, we end up using the differential form of an equation, right? But to get accurate results, if the options are very, very close together, do it the analog way, okay? Do it normally, do not use the differential way. I'll tell you why. Alright, I can see now that, well, a lot of people have solved it. Abhinandan got B, Bikash got C, Archana B, alright, Shraddha, Sharda B, okay. Anybody else? What are we doing with this question? Momentum of an electron is changed, right? Okay, by delta P. De Broglie wavelength is changed by 0.5%, that is given here. We have to find out initial momentum of the electron. Okay, let's see how to solve this. So, first things first, we know the relation between them. We know that lambda is equal to h by p. This is the relation that we have, relating wavelength and momentum. Okay. And now that changes are given to us, right? So, let's say lambda initial is equal to h upon p initial, right? And then lambda final will be how much? Final wavelength will be equal to lambda final, which is equal to lambda initial minus the change that happened, right? Because it says that it got, if you increase the momentum by delta p, then wavelength is going to decrease, right? So if I assume that momentum is increased, wavelength decreases, and wavelength decreases to how much amount? It decreases to lambda minus 0.5 upon 100 lambda, which is what? 1 upon 200 lambda. That gives you 199 by 200 lambda, right? Okay. But then what is lambda final? Lambda final will be equal to h upon final momentum, right? And final momentum will be how much? Final momentum will be initial momentum plus delta p. Okay. And once we get this, we can write, yes, h upon p plus delta p is equal to 199 by 200 into lambda. Cross multiplying, h cancels out over here, and we get, h cancels out over here, and we get p plus delta p is equal to 200 by 199 into p, which is equal to, yes, p comes out to be 100 times delta p, right? If p comes out to be 100 times delta p, that means delta p comes out to be p by 100. Delta p is equal to p by 100, right? And then, if this is the change, then how much is the final? The initial momentum of the electron will be how much? Yes, 100 times delta p. So, initial momentum of the electron, wait a second. Initial momentum of the electron comes out to be, yes, 100 times delta p. Alright, I think there was some error over here, so I can see that this should be actually 100 times delta p. Okay, I hope you all have understood this. Alright, now let's move on and let's go to the next subtopic over here, right? So we are looking at matter waves, right? And, well, what happens when we have a charged particle? Okay, so what happens when we have an electron gun and how much is the matter wave that comes out? So let's look at an electron gun more. Alright, so electron gun, yeah, what does the name tell you? Electron gun should actually give you accelerated electrons, right? That's what it is. Electron gun gives you accelerated electron. There is a vacuum tube and the electron beam comes and gets accelerated, right? So if there is a potential difference of V between the two terminals, then the electron gets accelerated by potential difference V, and yes, the energy, or rather the energy that is gained by the electron comes out to be E times V. E is, yes, charge of one electron. There we go. Now, for any charged particle, we understand that d Bruys wavelength is equal to h upon root over of 2 mqv, right? So, electron is just one particular type of charged particle. So, can we understand, yes, the same concept will be applicable for an electron as well, that is coming out of an electron gun. And to make matters very simple for you, right, आप लोगों के लिए matters बहुत easy करने के लिए, here we have substituted all of the values over here, right? And lambda for an electron comes out to be 12.27 divided by root V in angstrom. Alright? See, what have we done here? We have just substituted all of these values, right? Mass of electron, charge of electron, Planck's constant, all of the constants over here. And we get d Bruys wavelength of an electron when it is accelerated by a potential difference V. Okay. Now do remember this value. I will say definitely do remember this value, because whenever an electron gun comes in the question, you can directly substitute value of V in here. Okay. Easy to remember, 12.27 divided by root V. Right. And the wavelength that you get over here will be in angstrom. Now, why just for an electron? Right? If we can calculate, or if we can actually, substitute all the standard values and remember it for an electron, we can remember it for a proton also. Let's do that, right? So what I'm doing here, I am just substituting mass of a proton, charge of a proton, and Planck's constant, right? When I substitute that, if there is a proton that is accelerated with a potential difference V, then here we get, after solving all of this, we end up getting d Bruys wavelength of a proton is equal to 0.286 divided by root V. Alright? So, as I told you before, keep short notes with you, right? Yes, keep short notes with you. In that, make small notes for specific d Bruys wavelength of electron, proton, and next is going to come for alpha particle. Alright, because these are very common particles for which you are required to calculate it. Okay. Shruti here says only applicable for accelerated electron. Yes, Shruti. Here, when we are calculating de Bruys wavelength for accelerated charged particles. Okay. So accelerated electron, accelerated proton, and accelerated alpha particle. That's what we have here. Alright. Now, as I told you, we get to alpha particle. Again, the same thing. Mass of alpha particle is basically what? 4 into 1.67 into 10 to the power minus 27 kgs, right? Mass is 4 times mass of a proton, and charge is 2 times that. H is H, you know that. So when we substitute everything, we get again this, which comes out to be lambda is equal to 0.101 divided by root V. Alright, and here as well, lambda will be in angstrom. Angstrom is, yes, 10 raised to the power minus 10 meters. Okay, you know this. Alright, now that we know all of this, right, what have we done? We've studied the concept, we've understood the concept, right? We've actually calculated shorthand for calculations also, right? Now what do? We come to a question and we apply all of what we've learned, right? Come on, quickly solve this particular question. It came in NEET 2020, right? Quickly solve this, quickly tell me what the answer comes out to be, yeah? The question is, an electron is accelerated from rest through a potential difference of V volt. Alright, an electron is accelerated from rest. Potential difference is V volt. If the de Bruys wavelength of the electron is 1.227 into 10 raised power minus 2 Newton nanometer, the potential difference is, right, potential difference is 10 volt, 10 square, that is 100 volt, or 1000 volt, or 10,000 volt, right? That is the question. So, come on, quickly solve this. You have just seen the small calculations, right? Yes. So, after calculation, we have our shortcut. You just need to apply it. You just need to calculate the potential difference. And here, see, you've got easy options, right? They're basically trying to get to, you have very, very easy calculations with you, right? Okay, all right. You just need to figure out what order or what degree of potential difference is here. 10 volt, 100 volt, 1000 volt, 10,000 volt. All right. Mr. Crafty Bunny says, I am back. Yes, welcome back. Come on, start solving questions quickly. All right, I have one, yeah, option C. Prathar got D. Pratihar got D. Avantika got B. Okay. Let's see what the solution is. As I told you, just apply the basic, right? So what do we have? We have for an electron, lambda is equal to 12.27 divided by root V. Now, if you remember this, you can directly substitute, right? Root V is equal to 12.27 divided by the wavelength that is given here is 1.227 into 10 raised to minus 2 nanometers, right? So first you convert it into angstrom and then you substitute it over here, right? So when we convert it into angstrom, what do we get? Nanometer is 10 raised to minus 9 basically, right? So this will be 1.227 into 10 raised to minus 1 angstrom, right? Which is 0.1227. That's it. You substitute it, you get V is equal to 10 raised to 4 volt, which is option number D, right? Okay. Shruti, yes, nanometer is not in meters. Nanometer is 10 raised to minus 9 meters. Okay, so you got to remember all of that. Okay, and the answer comes out to be option number D. I hope everything's clear here. Yeah? Alright. Now that we have understood, well, de Bruys hypothesis, we've understood matter waves, let's go to Davison and Germer experiment. Okay? The next subtopic over here. And as I told you before, right, when I was talking about, well, de Bruys hypothesis, it was later proved in Davison and Germer experiment. So that's what happened, right? Earlier, when de Bruy gave his hypothesis, a lot of people did not, give him a lot of due. Alright, what they thought was, okay, you've just taken P is equal to H by lambda and you've taken lambda is equal to H by P and given it for matter waves. Right, where is the proof? The proof came here when Clinton Davison and Lester Germer, right, two scientists, they performed this experiment. Okay, so what is happening over here? Well, we have just seen what happens in an electron gun, right? What happens in an electron gun? You accelerate an electron till a certain potential difference and you fire those electrons with a good amount of kinetic energy, right? Now, the kinetic energy with which you fire those electrons will depend on how much potential difference you applied while accelerating the electrons, right? So here also what Davison and Germer did was they had an electron gun, they accelerated electrons and then they bombarded a nickel crystal with it. Okay, now why crystal? Well, the thing is, in case of a crystal, right, it's got certain structure, crystal structure, right? So nickel's got a certain crystal structure where the distance between the two crystal planes is similar to the wavelength that we have of these electrons, alright? So 2.51 angstrom is the distance between the two planes in the crystal structure, okay? Think of it that way, crystal planes. Now, what they understood was, right, you've got an electron beam that is being well fired at this and there is an angle theta that's being made with the crystal plane. Okay, so this electron beam, it gets reflected, and when you finally capture this electron beam, right, movable collector, there's a collector here, and when you actually capture this, you get certain very interesting results. All right, so okay, let's understand this very, very common sense. Okay, think about it. You have electrons, you bombard them, they get reflected. What kind of capturing should there be? You should just get a lot of electrons over here, right? Come on, think about it. If I have, well, an electron gun and I'm bombarding with electrons, right? You see at the very top I'm making this diagram, okay? So if there are a lot of electrons coming and I have a detector over here, then ultimately the detector should just detect a lot of electrons bombarded at a particular point, right? But here that did not happen. What happened? What happened over here was, in this detector, there were certain voltages for which a maxima was shown. Okay, so a maxima was observed, and that is where things got complicated. So let me give you more details. All right, so what kind of observation was there? If you take that same electron gun, right, and you change the potentials and you change the angles at which you're firing, right? That's what we do in an experiment. There are different parameters. So here we've got potential difference by which we are accelerating and the angle at which we are firing. So they started changing them. Say they started with 44 volts, then they went to 48 volts, then they went to 54 volts, and what they saw was, see, intensity, right? There is a peak in intensity that they observed. In case of 44 volts, a very small peak, then that peak increased, then that peak increased to a maximum size at 54 volts and 50 degrees. All right, 50 degrees is the angle at which the electron beam hit the crystal plane. Okay. Then if they kept increasing the voltage, say 60 volts, 64 volts, 68 volts, you see that the peak decreases, right? Yes. So what they said was, wow, what is happening over here? Why am I getting a peak? Right? So that is not particle behavior, right? And what we understand from here is that this is not particle behavior. This is actually electron beam coming in, right? Hitting the crystal plane, getting diffracted from crystal plane, and then interference happening between the two diffracted waves, right? Just like we saw in YDSC. Light wave comes in, right? There were two slits. Light wave comes in, right? Gets diffracted from these two slits, and then these two diffracted waves, they interfere and we get a pattern on the screen. So the same thing's happening over here, right? Okay, I'll go back to this diagram, and here you will be able to see, right? So what has happened here? Diffraction happened and a pattern appeared, right? A peak appeared, peak intensity. What does it mean? It means that here we have got electron waves that are undergoing diffraction and interference and giving a maxima peak, right? Okay. And that is what proved that matter waves can exist. Here we've got the experiment proving existence of matter waves. And with calculations also, all right, with calculations also, we understand that. See, if we calculate de Bruys wavelength, all right, so now pay attention again. Till now, we understood the theory behind it. Now, let's understand with the calculation also. See, if we calculate de Bruys wavelength of an electron that has been accelerated by potential difference of 54 volts, right? We calculate it by using our well shortcut. We get lambda is equal to 12.27 divided by root V, which is equal to approximately 1.67 angstrom, right? Now, keep this in mind and let's see what is happening inside the crystal structure. Okay, so here we go. If the incident beam comes like this, electron beam, reflected wave goes like this, right? Then do you see that the first one, now I'm naming them, first one and the second one, right? First one and the second one have a path difference here. Do you see this? First one and the second one have a path difference, and this is the path difference, right? This distance and this distance, add them up. This is the extra amount that the second wave is traveling compared to the first one, right? And now, okay, I'm not going to go into detail, but I'm going to tell you very quickly that one law, right? There is Bragg's law for crystallography, okay? That is applicable only for waves, okay? So Bragg's law for waves, which says that if path difference is integral number of wavelength, integral value of wavelength, then you're going to get a maxima, okay? That the electron beam also starts to apply. Alright, so यहाँ पे ये जो Bragg's law है, एक law होता है, alright, जो कि waves सिर्फ follow करती हैं और crystallography में काफी यूज किया जाता है. आपके सिलेबस में नहीं है, but काफी यूज होता है एक्सरेज को डिटरमाइन करने के लिए, ठीक है? तो उसमें अगर हम यहाँ पे इन दिस पर्टिकुलर एक्सपेरिमेंट द इलेक्ट्रॉन वेव ऑल्सो स्टार्टेड फॉलोइंग इट, ओके, एंड दैट इज द मोस्ट एक्साइटिंग पार्ट. हियर आई विल टेल यू हाउ, ओके? सो द पाथ डिफरेंस ओवर हियर कम्स आउट टू बी हाउ मच? पाथ डिफरेंस कम्स आउट टू बी, एज यू कैन सी, यहां से बीम आ रही है, यहां से जा रही है. इफ दिस एंगल इज थीटा, देन this is the path difference, right? D sin phi and D sin phi over here. Phi is the angle at which you have bombarded the electron beam and the crystal plane, okay? Angle between the electron beam and crystal plane. So if this is the path difference, which is D sin phi plus D sin phi, which is 2D sin phi, if this is equal to n lambda, then we understand that we get a maxima, okay? Long story short, now I'm going to say everything in short, ठीक है? कोई अगर confuse हो गया हो तो do not worry. What I'm saying over here is 2D sin phi, ये जो path difference है, ये n lambda के बराबर अगर आता है, if this is equal to n lambda, then we get a maxima. If I substitute n is equal to 1 here, I get lambda is equal to 1.66 angstrom, and in Davison and Germer experiment, see, the wavelength that you calculate by applying Bragg's law, which is there for X-ray crystallography, you get the same value of wavelength as you get from the Bruys equation. Do you see the difference? You see that 1.66 angstrom we got from Bragg's equation, 1.67 angstrom we got from de Bruys equation. What does that mean? It meant that in that experiment itself, Davison and Germer, they proved that the equation that is applicable for waves is applicable for the electron wave as well. So of course, electron ka wave hoga, right? That's what it is. Understood? All right. So, अगर आपको टेक्निकल बहुत ज़्यादा नहीं जाना है उसमें, if you don't want to go to very technical, then I will say that just remember that 2D sin phi is the path difference that is equal to n lambda for maximum intensity. ठीक है? The way we have in wave optics, right? Okay. So then yes, very appropriate question. Kiran, how are questions asked in this experiment? Right? So questions एकदम simply पूछे जाते हैं, ठीक है? What they will say is, in Davison and Germer experiment, phi is the angle between incident beam and crystallographic plane. So the angle between crystal beam and incident beam and crystallographic plane will be given to you, right? And D will be given to you, distance between the two planes. You will be asked to find the de Bruys wavelength. Okay? So just remember this over here. This is a formula that you need to remember for any numerical based on Davison and Germer experiment. Okay, either D and phi are given to you and you are asked lambda, or well, 2 out of 3 things will be given to you and the third thing will be asked. Alright? Is this clear? Okay. Alright. Let's move on now. So, what have we understood till now? Well, let's recap everything. Okay? First things first, what are the observations? The observations are, we observed variation of intensity with theta, we observed a peak at a particular voltage and a particular theta, and applying Bragg's law, we figured out that there is a constructive interference happening. Constructive interference of electron beams, electron waves for that matter. Okay? Alright. Now, here in this particular experiment also, lambda comes out to be 0.167 nanometer, and in general, right, for any electron gun, this is how you calculate the value of de Bruys wavelength. Okay? Alright. Now that this is done, right, let's move on to our next and last subtopic of today's lecture. Alright? So, as you can see, well, I would say, if you've understood everything, I hope you have other friends as well, right, that will need this video. So do share this with them. And let's move on to the last subtopic of today's session, which is Heisenberg's uncertainty principle. Alright. So Heisenberg's uncertainty principle, what does it say? Well, as the name suggests, we are talking about uncertainty. Now, uncertainty in position and momentum. Alright. So, think about it that way. First things first, Heisenberg's uncertainty principle says it's not possible to accurately tell the position and momentum of an object. Alright. So, why does uncertainty principle come about? Well, the thing is, think about it, matter waves, right? So, every mass, or rather every particle, right, whether it is big or small, going fast or slow, it will have a corresponding matter wave of it, right? Right. So that means there is wave nature, there is particle nature. Now, when I talk about a particle, right, I can say that a particle can exist in single place at a given instant of time, right? But only if it is only a particle. But now that we've understood that, well, nothing in anything that has mass, or rather doesn't have mass as well, it is going to behave like a wave as well, right? And what happens with wave? A wave will not be at a single place at a given time, right? It will not be. So then, when I talk about, well, wave-particle duality, when I talk about matter in general, I'll have to say that for any particle out there, since it exhibits wave nature as well, and certain times it exhibits wave nature as well, it will not exist at a single place, or rather, the probability of it existing at a single place at a given time varies with its nature, right? Exactly. And that is where the uncertainty comes in. Alright, if it does not stay at one place at any given time, if I cannot tell what its position is at any given time, that means there is uncertainty in position, right? Similarly, there is uncertainty in its momentum. So, if we talk about the mathematical relation that we have over here, right? So, think about it this way. We have momentum. Momentum of a wave is h by lambda. And we have momentum of a particle, that is mass into velocity, right? So, when we have a particle, so the probability of it behaving like a particle will tell you the probability of its momentum being equal to mv. Make sense? And the probability of it behaving like a wave will give you probability of it having momentum h by lambda, right? Alright. Now, as soon as we talk about probability, we talk about, yes, it is not equal to a certain value at all the time, right? When we talk about probability, it is not certain. So, uncertainty comes into the picture. Do you understand? And that is why we will say that for every day, well, every object will have uncertainty in position and momentum. It's just that for everyday objects, since wave nature is, well, just, na ke barabar hai, that is why we will not be able to notice uncertainty in position in case of everyday objects. All right. So here is a mathematical relation. It says if delta x is the uncertainty in specification of position and delta p is uncertainty in specification of momentum, then delta x into delta p is greater than equal to h upon 4 pi. Okay, delta p into delta x is greater than equal to h upon 4 pi. Remember this. All right. Okay. Now that we've understood this much, now you must be wondering, ma'am, what kind of questions come? Let's do questions. So of course, let's do questions. And as I've told you, well, we have understood properly, right? What is uncertainty in position? What is uncertainty in momentum? But then when we apply them, right? In exam, when numericals come, numericals will come based on this particular equation. All right, or rather inequality. Delta x into delta p is greater than equal to h upon 4 pi. If you want to have an equality, or rather you want to find out the extreme case, you will have to apply the equality. Okay, so in case of extreme case, delta x into delta p will be equal to h upon 4 pi. Okay. Now, let's solve this question. Quickly, come on guys, solve this question. Tell me what the answer comes about. Try to solve it within 1 minute, okay? As I always say. The question is, position of a chloride ion on a material can be determined to a maximum error of 1 micrometer, okay? If the mass of the chloride ion is 5.86 into 10 raised to minus 26 kgs, what will be error in velocity measurement? Okay, we're talking about error, right? Error will be extreme case of uncertainty. Okay? Alright, let's apply this. We've just understood the equation. What will be the answer? Option A, B, C, D. Come on guys, quickly calculate, quickly tell me the answer. Let's see what the answer comes about. Okay, Sharda got an answer, B. Come on guys, quickly calculate, quickly tell me the answer. This is a simple application of Heisenberg's uncertainty principle, alright? Now, actually in theory, the principle goes way beyond what we've learned, alright? But in our syllabus, you just have to deal with one inequality, okay? That's it. Let's see, let's look at the solution now. Position of a chloride ion on a material can be determined to a maximum error of 1 micrometer, right? Maximum error, delta x is 1 micrometer. Micro, 10 raised to minus 6. Okay, so delta x is equal to 1 micrometer and mass of chloride ion is already given 5.86 into 10 raised to minus 26 kgs. And we already know delta x into delta p is greater than equal to h upon 4 pi, right? So, what do we get? We can substitute everything and we can say that delta x is this into delta p. Delta p will be what? Mass into delta v. Delta p is equal to mass into delta v. Right. We substitute over here. We get this is greater than equal to h upon 4 pi. We substitute everything. Cross multiply. Solve. Here we go. The answer comes about. Delta v is greater than equal to 9 into 10 raised to minus 4 meter per second. That means the minimum error in velocity will be 9 into 10 raised to minus 4. There we go. Option number D is the correct answer. 9 into 10 raised to minus 4 meter per second. Okay. See, what I'll tell you, एक line में is that make sure you are not making any calculation errors. Alright. There will be questions where you have bad calculations coming. Now, you've understood the application, you've understood the concepts, and this is where I will end the session. Here, I've got the mind map for you, alright? So, matter waves, what is de Bruys wavelength? H upon P, which is equal to H upon mv. kinetic energy and momentum relationships, de Bruys wavelength in terms of kinetic energy and in terms of potential difference by which a charged particle is accelerated. And Bragg's law for waves, as I've told you, well, in Davison and Germer experiment, if you get a numerical, it will be based on this. Alright, 2d sine phi is equal to n lambda. Remember this. And last but not the least, Heisenberg's uncertainty principle. Now, do not forget to go back and revise the notes properly and revise NCERT properly. Do practice. When you practice questions, do practice with time limit. All right, give 60 seconds, maximum 60 seconds per question. Now, tomorrow we will have another one shot at 3 p.m. and we will be doing photoelectric effect. All right. So, till then, happy learning. See you tomorrow.